Morning, everyone. Questions while we wait for everybody to come in? How are we doing with the material? You know what to do. Writing on a tablet is going to be fine as long as it's in your handwriting, right? I don't want anything typeset or anything. Here we're talking about the derivative of a product of four functions together. You know what to do, right? I mean, if you don't know what to do, then do this. Group them into uv times wz. Then you've got a product of two functions. So it's going to be a product rule. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. But now the first one is itself a product. So product rule applies here. So u prime v plus uv prime times wz. And similarly, this wz is a product. So product rule applies. W prime z plus wz prime. And if you expand all of that, not that you have to, because this would be sufficient, but if you expand everything to see what's happening, what has happened? You had UVWZ, differentiate the first one, leaving the other ones fixed. Differentiate the second one, leaving the other ones fixed. Plus, differentiate the third one, leaving the other ones fixed. Plus, differentiate the fourth one, leaving the other ones fixed. Sort of a generalization of the product rule, if you will. Benjamin wants to discuss the greatest integer less than function. And it's exactly that, greatest integer less than or equal to. Greatest integer less than or equal to x. Example. Greatest integer less than or equal to 1/2. You know the integers are the whole numbers and their negatives, right? So the integers denoted by z. -3, -2, -1, 0, 1, 2, 3. So what is the greatest integer less than or equal to 1/2? Well, 1/2 is between 0 and 1. So the greatest integer less than or equal to is going to be 0. Greatest integer less than or equal to e. E is 2 point something something. So it's between 2 and 3. Greatest integer less than or equal to is 2. Greatest integer less than or equal to 3. Well, that's 3 itself. Because 3 is an integer. Minus 1.2. Minus 2. And so on and so on. Danielle wanted the derivative of x over x plus c over x. Well, I mean, x over x is just 1, right? As long as x is not 0, but x can't be 0 here either. So you could simply rewrite it this way. Well, let's, right, very well. So if we rewrite it this way, this is going to be minus c over x squared. This is valid as long as x is not 0. Oh, that's not what it was. X over x plus c over x. Very well. Let's do that. Maybe we want to simplify that first. Right, we're looking for the derivative of this. If we put everything over a common denominator, first of all, here x cannot be 0, right? So we want to stay away from that. If we put everything over a common denominator, this is actually x squared over x squared plus c. And this is valid for x not equal to 0. Very well. If c is not 0, let's take the derivative of this, see what happens. So it's a quotient. Quotient rule applies. vu prime minus u v prime all over v squared. This is 2x cubed minus 2x cubed. These cancel out. And we're left with 2xc over x squared plus c all squared. I suggested we should discuss when c is not 0. So we get this. But notice that if c is 0, this is really just 1 whose derivative is 0. But if c is 0, this is also 0, so no harm done. That's the answer. Why is the numerator x squared? Well, you tell me. We're always learning something new, right? All right. Questions here? The midterm review tomorrow will be recorded. It's my understanding a lot of you have a conflict, have another class. questions here? So, I mean, if you have questions about midterm material, please ask me today, because as soon as the midterm opens up, I will not be able to discuss any midterm material. I want to go over the first step. All I'm doing is simplifying. I suggested we simplify before differentiating, right? So x over x plus c over x, common denominator. And when you divide by a fraction, you multiply by the reciprocal. I'm not sure what time the midterm review is at. It's everything's posted on my courses. How many questions on the exam? I want to say 17 questions. I'm not 100% sure though. Step 2 to 3. What are we doing? Here to there? Or 2 to 3? 1, 2, 3, there. Either way, it's all the same. C is just a constant here. C is only a constant. Fred, did you have a question? Tina, derivative of cos x sine x, 3 to the x, 3x. This is the question from here to there. Come on, is that your question? All I'm doing is I'm expanding. Open up the brackets, multiply everything. Some stuff cancels out and you're left with that. Derivative of this, well, you recognize you have three things multiplied together, right? So you know what to do. We'll differentiate the first one, leaving the other two fixed. Plus, leave the first one fixed. Differentiate the second one, leaving the third one fixed. Plus, leave the first two fixed. Differentiate the third one. There it is. All right. Questions? Moving on. Oh, there was a tangent line. Did somebody erase it? Slope of the tangent line, something. You can differentiate the first two and do a product rule for the third, absolutely. I think it was removed. So, I mean, as you know, Jordan, the derivative gives you a rule for the slope of the tangent line. Maria's asking if that would be the final answer. Well, I mean, depending on what you want to do, right? I mean, you could rewrite this as cosine squared, and this is minus 3x sine squared x. But, I mean, it doesn't simplify very much. Does the derivative exist? I claim it does not. Right, Benjamin? The better question, though, I think, is this. This would be an excellent midterm question. Did we do this question in class? Did we discuss this question before? No. Very good. Let's discuss it now. It's a great question. Find f prime of 0 or show it does not exist. Well, I mean, here's the thing. Right, if you differentiate x squared, x squared sine 1 over x, you know what the derivative of that is. Right? I mean, it's a product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. And this is the derivative. This is the derivative everywhere except at 0. Right? And now, maybe you're thinking to yourself, well, if I take the limit as x goes to 0 of this, if we consider the limit as x goes to 0, let's look at the two pieces separately. Let's look at this piece. Taking the limit as x goes to 0. And you know that sine is always between -1 and 1. So if you multiply the whole equation by 2x, well, now it's going to depend on whether x is bigger than 0 or x is less than 0. So if x is bigger than 0, and you multiply by 2x, then what happens? You get minus 2x. And as x goes to 0, this goes to 0, and that goes to 0, so the stuff in the middle goes to 0 by the squeeze theorem. And similarly, if x is less than 0, then what happens? If x is less than 0, and you multiply by 2x, then the inequality reverses. But you still have a squeeze theorem happening. Both sides still go to 0. So the stuff in the middle goes to 0 as well. So limit from the left and limit from the right are both 0. This limit is 0. But this limit as x goes to 0, 1 over x goes to some sort of infinity. So what happens? If x goes to 0 from the right, this goes to positive infinity. And what is cosine of positive infinity? Well, you know what cosine looks like. And you know that the limit doesn't exist. This isn't going towards a specific value, one unique value. So that limit does not exist. This limit goes to 0. That one does not exist. So the whole thing does not exist. Which might lead you to believe that the derivative does not exist. But that's not correct. And that's why this would have been a beautiful midterm question, because it's a trap. How would you know you need to use a squeeze theorem? Well, here you have a limit of 0 times does not exist. And this is a suggestion that possibly the squeeze theorem might come into play. Right? So if you conclude that the derivative does not exist, it's incorrect. It's incorrect because that has nothing to do with the derivative at 0. All we're showing here, well, I don't even want to get into what we're showing. Why did I start by taking the derivative? Because that's what a lot of people want to do. A lot of people want to take the derivative and then take the limit of the derivative. And that's no good. Here, the derivative at 0 is just the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. And what is that? F of h is h squared sine 1 over h. F of 0 is 0 over h. So you see, this is just the limit as h goes to 0 of h sine 1 over h. And this limit is exactly this part, which we showed was equal to 0. So in fact, the derivative at 0 does exist, and it's 0 by the squeeze theorem. And this is a nice example that shows, what does it show? What does this show? This shows that the limit of the derivative this does not exist, so it's not equal to the derivative at 0. In other words, the derivative is not continuous here. The derivative is not continuous. That's all that shows. You have to use the limit definition in order to find the derivative here. You cannot find the derivative and then take a limit, because the derivative is not continuous. Benjamin, where did I lose you? The derivative at 0 does exist. The derivative at 0 is equal to 0. But the limit of the derivative does not exist. So the derivative itself is not continuous. Matt, I'm not sure what you're saying here. What does the limit of a derivative generally show us? It shows us whether the derivative is continuous or not. And that's what a lot of people misinterpret when looking at this question. Right? I mean, you know that if a function is differentiable, it had to be continuous to begin with. But it doesn't tell us that the derivative itself has to be continuous. It's the original function, not the derivative. Where did h squared sine 1 over h come from? It came from here. It's your f of h. For h sine 1 over h equals 0 sine 1 over 0. For f prime of 0, I never wrote that down. But what I'm showing here is that this limit is equal to 0. That's the work that we had originally done right here, except for that 2. How we got 0 from the squeeze theorem, we started with sine 1 over x between -1 and 1. And we multiplied by, in this case, 2x, because I was doing this one. If you want to do just h or just x, then you would just multiply by x. But you want to be careful, because these signs are going to change depending on whether you multiply by a positive number or a negative number. All right, people. Why don't we do the squeeze theorem again? Seems to be causing a lot of issues. Not sure why, because we have seen this example before. Let's consider this limit and prove it. Plug in 1 over h. As h goes to 0, this is going to be some sort of infinity. Sign of either positive or negative infinity does not exist. So this has the form 0 times does not exist. Who knows what happens then? But we're hoping that the 0 is strong enough to make everything be 0. What do you know about sine? You know sine is always between -1 and 1. Sine is the problem here, right? Because the limit of the sine does not exist. So we ask the question, can we get rid of it? And we can by squeezing it between -1 and 1. So now, multiply this by h to get this. Well, sorry. I'm a bit hasty there. Sine of theta is between -1 and 1. So sine of 1 over h is between -1 and 1. And now multiply everything by h. But now that's going to depend on, right? The product is going to depend on what h is. We're taking the limit as h goes to 0. So we're going to have to break this up into limit as h goes to 0 from the right and limit as h goes to 0 from the left. Because when you multiply by h, the sign may change depending on whether h is positive or negative. So let's take this limit. In other words, let's assume h is bigger than 0. When h is bigger than 0, the inequality remains. And now, as h goes to 0 from the right, this goes to 0, this goes to 0, so the whole thing goes to 0 by the squeeze theorem. I'll let you repeat for the limit from the left, but there it is. All right. Jordan's asking why we need to take the limit of the derivative. We do not. That's the whole point. We don't. We don't, but a lot of people want to. And then they get the answer wrong. Limit from the left, the inequality sign switch, exactly that. Benjamin was asking why we have to break it up into limit from the left and limit from the right. That's because when you multiply by h, since h is close to 0, it could either be positive or negative, and that's going to alter the sign. If you multiply by a positive number, the inequality remains. If you multiply by a negative number, the inequality reverses. Either way, though, the squeeze theorem is going to work. And as Matthew points out, if the limits did not agree, then the actual limit would not exist. But limit from the right is 0. I'll let you work out the limit from the left, but it does turn out to be 0 as well. All right, how are we doing here? Moving on. If we don't find the limit of the derivative, what are we supposed to do instead? Somebody want to address that? Use the definition, use the limit definition of the derivative. Exactly that. Very well. Let's move on. Jessica is asking if the limit from the left and right both equal 0, how is it not continuous? Somebody want to address that? Maxwell, it could happen. Absolutely. Absolutely. I mean, the 0 is the easy case, but in the questions in the back of the book, you've got examples where it's not 0. Jessica, back to your question. You're referring to two different things. We took limit from the left and limit from the right in order to figure out what the derivative of the function at 0 was. The other case, what is not continuous? It's not the function that's not continuous, but rather the derivative. Here, this is not the limit of the derivative. It's the limit definition of the derivative. All right, moving on. Moving on to what we were looking at last time. Well, I mean, we kind of started looking at word problems, which are known as related rates. So the derivative of f at 0 is 0. Exactly that, Sean. You will not be allowed, well, I mean, you can always ask whatever you want. I will not be answering questions from Friday to Monday related to midterm material. Midterm is released at 9 a.m. on Friday. We still have a lecture on the day of the midterm. It's all good. Exactly that, yes. The derivative itself is not continuous in this case. Absolutely. So we've started looking at related rates. As the name suggests, it's rates that are somehow related. And it's best to just consider some examples. There's nothing more to say about that. A stone is dropped in a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Find the rate at which the area within the circle is increasing after 3 seconds. I know everybody is excited about the midterm. If you know the material, midterm will be very easy. Relatively easy. We'll be fine. You'll be fine. I mean, you do have 3 days, right? Any word problems on the midterm? I don't think so. I don't think so. I believe it's something like 17 questions. I could be wrong. Could be very wrong. But something like that. All right, so you see what's happening, right? You've got this lake and you drop a stone and it's going to create a circular ripple, which, I mean, the wave moves out at a rate of 60 centimeters per second. So let's introduce some variables here. No multiple choice. Right, so let's introduce some variables to describe what's happening here. Let's introduce some variables to describe what's happening. Right, I mean, you're going to have some circular ripple with some radius, r, and it's the r that's traveling at a rate of 60 seconds. The rate of change of r, or dr dt, is 60. Right, so dr dt is given, and what is the question asking? The rate at which the area is increasing. So the rate of change of the area. What is the rate of change of the area? And you know the rate of change is the derivative. So what is the derivative of the area with respect to t? So what is dA dt? Well, I mean, if we can relate the area with the radius, can we find a relationship between the area and the radius? And as you know, right, I mean, you've got a circular ripple. So the area of the circle, what's the area of a circle? Area is pi r squared. Absolutely. And what do we want? We want the derivative with respect to t. So differentiate the whole thing with respect to t, with the understanding that the radius itself is some function of t. We never worked out what it was, but it doesn't matter. It's some function of t, right? As time increases, the radius is getting larger and larger. But whatever, you don't need to figure it out. All the information we need is right there. Differentiate the whole equation, so left-hand side becomes dA dt. Pi is just a constant. This is something squared, so the derivative is 2r, and then you differentiate the inside, right? Chain rule. The inside, the derivative is dr dt. What do we want? We want the rate of change after 3 seconds. Have I introduced this notation? If not, let me introduce it now. So the rate of change of A with respect to t when t is 3, and when t is 3, well, what is the radius? After 3 seconds, if the radius is increasing at a rate of 60 centimeters per second, after 3 seconds, the radius will be 180 centimeters, absolutely. So dA dt, when t is 3, pi times 2 times 180, and dr dt was given to be 60, and there it is. This is the rate of change, whatever that is. That's the rate of change of the area when t is after 3 seconds. How are we doing? A big number for sure, yeah. But that's the idea behind related rates. You have to find some relation between what they want and what they give you. That's all. That's all it is. Thank you. The radius of a sphere is increasing at a rate, the radius of sphere increasing at a rate of 4 millimeters per second. How fast is the volume increasing? When the diameter is 80 millimeters. All right. So you see what's happening, right? You've got this sphere, and the radius is getting larger and larger. I mean, maybe a balloon that you're blowing up. And the radius is changing at a rate of 4 millimeters per second. How? So, I mean, if the radius of the balloon is changing, so is the volume. What is, or how fast is the volume increasing? How fast is the volume changing when the diameter is 80? Don't be fooled here. Or the radius is 40, right? And what do they want? How fast is the volume increasing? Right, so first of all, it's important to pinpoint what the question is asking. How fast is the volume increasing? What does that mean? They want the rate of change of the volume. What is dV dt? That's what they want. What is given? The radius is increasing at a rate of 4 millimeters per second, right? You see per second per unit of time. So dr dt, the rate of change of the radius, is given to be 4. So dV dt is what they're looking for. Dr dt is what's given. Is there a relationship between the volume and the radius? Well, of course there is, and you know exactly what it is. As Matt has pointed out, the volume of a sphere, 4/3 pi r cubed. So differentiate the whole equation with respect to t. Left-hand side will be dv dt, exactly what you want. What about right-hand side? This is just a constant. So leave that aside. Derivative of r cubed is something cubed. So 3r squared times the derivative of the inside. dr dt. Chain rule, right? Always the chain rule. What do we want? We want the rate of change when the radius is 40. So plug in 40 for the radius. First of all, these cancel out. That's 4 pi, radius 40 squared, dr dt was 4, and there you have it. (16 times 16 is 256 with 2 zeros. Is that right? Well, it's probably never a good idea to find a decimal expansion for pi, because it's always going to be an approximation. You can clean it or leave it in terms of pi. If this was an in-person exam, no formula sheets. You have to know everything. And that's the problem with these online exams, right? Now you don't have to remember anything, you don't have to learn anything, and it's a problem. Yeah. It's a problem because at some point we're going to go back to in-person exams. Well, I mean, what I mean by that is that you don't have to learn anything. What I mean is, if you do enough exercises, everything becomes second nature. You remember everything. You remember the derivatives of all the trig functions, of all the inverse trig functions, you remember volumes, because you've used them over and over again. I mean, the first time you might look up the volume of a sphere, but then when you do another question involving volume of a sphere, okay, maybe you'll look it up again. But after having looked it up 3 or 4 times, you're going to remember, and you're going to stop having to look it up. So that's what happens. So if you've been doing that, then you've been tackling this course as you should, and everything is going to work out great. I understand that a lot of people don't feel that's necessary, and you can still do well not doing that, but it's a disservice, because when in-person exams come back to be a thing, if you have developed terrible habits, yeah. I think so, Benjamin, exactly. All right, let's do a few more. The snowball melts such that its surface area is decreasing at a rate of 1 centimeter squared per minute. Find the rate at which the diameter decreases when the diameter is 10 centimeters. All right. Questions? You see what's happening, right? You've got the snowball melting, and what's given is the rate of change of the surface area. And this surface area is decreasing at the given rate. What do they want? They want the rate of change of the diameter. So the rate of change, what is the rate of change of the diameter? Do I want to call it DI so that it's not awkward? Does that make it even worse? Who knows? And what's given, exactly as Benjamin suggests, the derivative of the surface area. The rate of change of the surface area. Snowball melts so that its surface area is decreasing at a rate of 1 centimeter per minute. Now here, the previous question, we had things that were increasing, right? And we had positive rates of change. Here, if you want to denote the decreasing part, we're going to denote that by a negative, right? It's the opposite of increasing. It's decreasing, so the opposite of positive is negative. The rate of change of the surface area is -1. Now, is there a relationship between the surface area and the diameter? That's my question to you. What is the surface area of a sphere? Well, you know what it is. Surface area of a sphere is 4 pi r squared. Is it? Right, well, as Sean points out, there is a relationship between surface area and radius. We don't want radius, we want diameter. But of course, you know that the diameter is twice the radius. So you can rewrite this as pi times 2r all squared. And 2r is the diameter. So pi di squared. Exactly that. So you see, you have this nice relationship between the surface area and the diameter. What are we given? We're given the rate of change of the surface area. Let's differentiate this whole thing with respect to t. So on the left-hand side, the rate of change of the surface area, right-hand side. Pi is just a constant. The derivative of this is something squared, so 2 diameter times the derivative of the inside. The derivative of the diameter with respect to t. Now this, here they're mixing it up a bit, right? Normally we would be solving for this, but in this case we're solving for this. This is actually given, so that's -1. 2 pi, we're looking for the rate of change when the diameter is 10. So plug in 10. And you see that the rate of change of the diameter with respect to time, when the diameter is 10, is equal to -1 over 20 pi. How are we doing here? Everybody with us? What happened to the 4? Well, 4 is just 2 squared. Right? Expand this, you get 4r squared, 4r squared. All I was trying to do was relate the surface area and the diameter. Some people suggested that r was di over 2, so you could have plugged it into here, and you would have gotten di squared over 4, and the 4's would have canceled, bringing you to this stage as well. There are many ways to view it. It's all the same. Yeah. Sean is suggesting you could have left it like this, found dr dt, and then use this to relate dr dt to di dt, and that would have worked there as well. So, whatever is easiest for you. There's no unique way to tackle these. If you see a relation, go with it. And that's the whole point of these questions. It's relating one thing to the other. Consider the following. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers an hour, and ship B is sailing north at 25 kilometers an hour. How fast is the distance between the ships changing at 4 p.m.? How are we doing here? Exactly. Let's set this up. Let's set that up. So at noon, ship A is 150 kilometers west of ship B. So ship A here, ship B there, and this is 150 kilometers. Ship A is sailing east at 35 kilometers an hour. So here, ship A is going this way at 35 kilometers an hour. 35. And ship B is sailing north at 25 kilometers an hour. Right, so you see what's happening. First of all, let me point out, this is at noon, so 4 hours later, right, here you will have traveled at most 140 kilometers. So you'll still be in this region, right? So for the whole 4 hours, you're somewhere here, whereas B is moving up. So, you know, at any stage, you've got this right angle triangle. And what are we looking for? We're looking for the rate of change of the distance between the two. So we're looking for the rate of change of the hypotenuse. Something like that, absolutely. Right, so I mean, you have a lot of options. You have a lot of options, whatever you want to do. I mean, you could denote, what do we want to denote? So look, I mean, you have a picture of what's happening. You want to introduce some variables. What do we want to introduce? We can let little a be the distance traveled by ship A, and let little b be the distance traveled by ship capital B. Right? So here, at any time, this is going to be the distance B. A is the distance traveled by ship A. So big ship A is going this way. So this is going to be the distance traveled, A. So this side must therefore be 150 minus A, because the whole thing is 150. And now you have a right angle triangle with sides 150 minus A and B. So by the Pythagorean theorem, are we back? Excellent, thank you. All right, so right angle triangle, where the distance is the square root of this. What are we looking for? We're looking for the rate of change of the distance. We want the derivative of this thing. So what is that? Well, we want this at 4 p.m. So what is that? Differentiate. So differentiate this. What do we have? We have a square root. So the derivative of the square root is 1 over 2 square root times the derivative of the inside. Well, what do we have inside? We have 150 minus a all squared, whose derivative is, so it's a square, 2 times 150 minus a times the derivative of the inside. 150 is a constant, so times the derivative of the inside minus dA dt. Plus the derivative of b squared, so differentiate the square, 2b times the derivative of the inside, dp dt. Where a was the distance traveled by ship A, and ship A was going at 35 kilometers an hour. So dA dt is 35. B is the distance traveled by ship capital B. And ship capital B was going at 25 kilometers an hour. So dB dt is 25. And after 4 hours, if A is the distance traveled by ship A, after 4 hours, you will have traveled, what, 140 kilometers. So if we plug in 4 p.m., A will be 140. So that's 1 over 2. And B, after 4 hours, you will have traveled 100 kilometers. Sorry. Times A is 140, so that's 2 times 10. dA dt is 35, so that's negative 35. Plus B we said was 100, so that's 200 times dB dt, which is 25. What is that? That's 1 over 20 square root of 101. 700. 700, what is that, 5,000? 5,000 minus 700, so 4,300. Is that right? The zeros cancel out. 215 over square root of 101. Is that correct? Anybody? Could be wrong here. Does anybody have that? Thank you. How did I get the 101? We are looking at square root of 10 squared plus 100 squared. 10 squared, of course, you know is 100. So now I can factor out 100. And that is 1 plus 100. And square root of 100 is 10. Questions here? Anyone? Do we have time for one more? One more? Anybody? If nobody wants one more, we'll do one more. 18. A spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks, well, let's just draw some stuff. So we have a spotlight on the ground, shines on a wall 12 meters away. So we have a wall right here 12 meters away. If a man 2 meters tall walks from the spotlight towards the building, a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6 meters per second. How fast is the length of the shadow on the building decreasing when he is 4 meters away from the building? We'll finish that quickly. Right, so you see what's happening. If the guy is very close to the spotlight, you're going to have a huge shadow. And as he gets closer and closer to the wall, the shadow is getting smaller and smaller, right? So the shadow is decreasing at some rate. How fast is the shadow decreasing? When the guy is 4 meters away. So at the exact moment, the person is 4 meters away from the wall. All right. So let's introduce some variables. Maybe we can let x be the distance traveled by the guy. So x is how far the guy is away from the spotlight, or let x be the distance traveled. Distance traveled. What's given? Well, the rate of change, how fast he's moving, is 1.6. And if we denote, let y be the length of the shadow, right? So when he's close to the wall, the length is very large. When he's closer to the wall, when he's closer to the spotlight, the length is very large. When he's closer to the wall, the length of the shadow is smaller. What do we want? We want how fast, or the rate of change of the shadow. When the guy is 4 meters from the wall, so when x is 8. Right? So we've introduced some variables. We asked the question, what does the problem want? The problem wants dy dt. And it has given us dx dt. So really the question is there a relationship between x and y? If so, what is it? What is the relationship between x and y? Well, consider this. What do we have here? Here we have a right angle triangle. In fact, we have 2 right angle triangles. Right? 2 similar right angle triangles. If you fix the angle theta here, you have 2 similar right angle triangles. What is tangent of that angle? Well, in the small triangle, right, this is x, and the guy is 2 meters tall. So opposite over adjacent, the opposite side in the small triangle is 2 meters. The adjacent side is x. But in the large one, the opposite side is y. And this base is 12. And there you have it. You have this nice relationship between x and y. Y is 24 over x. What do we want? We want dy dt. Differentiate the whole equation with respect to t. Matthew, where did I lose you? Have I made a mistake? Is there a mistake here? We've labeled certain variables, x being the position of the man, y being the length of the shadow. The tangent part, well, you recognize that you have 2 triangles, 2 right angle triangles. This big one right here, where this is the length of the shadow, labeled by y, and this is 12, that was given. But you also have this smaller triangle, still with the same angle theta. So these are similar triangles. I'm calculating tangent of theta for both triangles, for both right angle triangles. And they have to be the same. So tangent is opposite over adjacent. So y over 12 in the large one. But in the small one, the guy was 2 meters. So 2 over x. And now we're restricting our attention to this, and that gives us the relationship between x and y. I'm not doing it for 4 meters in particular. You have to do it for any value of x, right? It's tempting to do it at one specific time, but you want, as Michael suggests, you want a general relationship, then you take the derivative, and then you plug in. You don't plug in first, right? In the same way that when you're looking for the tangent line, or when you're looking for the slope of the tangent line at a point, you don't plug in the point first. You find the derivative first, and then you plug in the point. Same here. So now if you differentiate dy dt, this is going to be negative 24 over x squared times the derivative of the inside, dx dt. dx dt was given to be 1.6. When you have traveled when you're 4 meters away from the wall, you have actually traveled 8 meters. So we're plugging in when x is 8. And what do we get? Minus 24. 8 times 8 is 64. Times dx dt, which is 1.6. And there you go. You get a negative answer, as expected, right? Because what's happening? The further away you are from the light, the smaller the shadow is. So the length of the shadow is actually decreasing, which is suggested by the negative. How are we doing? Questions? Anyone? Minus 0.6. I'll believe it. Thank you. There it is. All right. Well, thank you all for coming. Good luck on the midterm, and I will see you on Friday.